Welcome to the lecture series on process integration. This is module 6, lecture number 1. The topic of the lecture is placement and integration of distillation columns. You will see that we have talked a lot about integration and placement. Why we are doing integration with a heat exchanger network? Once we optimize a heat exchanger network, its fixed cost is almost constant, and if we want to decrease its cost further, then it is possible through decreasing the utility costs, and this integration with different other units gives that opportunity of decreasing the hot utility or cold utility. So, we will see in this lecture that how integration of distillation column with a hen or a process GCC will either reduce the hot utility consumption of the process, or with the same hot utility consumption will make the running of distillation column free. That means, the same hot utility will do the service of the distillation column in terms of providing the hot utility in the reboiler, and the condenser duty will also be taken care of by the process streams. So, let us see this placement and integration of distillation column. Pinch technology has established that good process integration practice pays off by bringing simplicity to the plant design and better use of energy. We have seen this in several cases. The study of distillation column using pinch analysis tools is the latest in the purview of pinch analysis, and this has been given by Dole and Linoff in 1993. It is called column targeting. This new approach facilitates identification of improvements in the column design as well as its synergetic integration with the background process. So, with this we will see now how exactly this is being done. Now, let us see what is the integration of column with background process. The traditional heat integration of distillation column with a background process is based on the appropriate placement of the column in the temperature pressure domain to make the best use of process streams in the reboiler and condenser. This has been told by the Smith and Linoff in 1988. Basically, when we see that the distillation column is working under two levels of temperature. Now, these two levels of temperature may be above the pinch of a process GCC, may be below the pinch of a process GCC, or may be across the pinch of a process GCC. Depending upon these two temperature levels, one level in which the reboiler is working, the other level where the condenser is working, will decide where the placement of this distillation column can be done. Often, however, the column box cannot be placed within the process composite curve. The result is that no decrease in overall heat load of the process is achieved. If you cannot do it, place it within the composite curve, then it is not going to decrease the utilities. it then becomes clear that it is the position of the column relative to the pinch that is significant. This we will see that where if I am placing the distillation column above the pinch, it will benefit, or below the pinch it will benefit, or across the pinch it will benefit. So, we will see this, that where the maximum benefit will take place, and accordingly we will decide a rule where to place the distillation column with a background process for integration purpose. Now, to integrate with the GCC of a process, it is necessary that the distillation column should be expressed in a TH diagram. Why? Because the GCC of a process is expressed in a TH diagram. So, if we want to integrate the distillation column with the GCC of a process, then it has to be also expressed in a TH diagram. Now, this shows a schematic distillation column. This is the bottom product, it goes to the reboiler, reboiler heated by a hot stream, and the vapor goes here. The feed is added to the distillation column here, and then the vapor goes here, it is condensed and heat is given out here, and the condensate is returned back to the distillation column as a reflux, and some part of it is used as a product. So, we have a product 1 and product 2 here, and this is reboiler where heat is goes inside it, that means this is a sink, and the condenser is a source where heat goes out. Now, this can be is working under two temperature levels, the hot stream temperature in the reboiler and the cold stream temperature here in the condenser. So, we can show a distillation column like this, Q reboiler is entering and Q condenser is going out. This can be further shown in a TH diagram like this. This is a box distillation column, this is the reboiler temperature in the temperature axis here, and this is the temperature of the condenser in the T star axis, is a shifted temperature, and Q reboiler enters into this and Q condenser goes out. So, this is the conceptual diagram of a distillation column in a shifted temperature curve and delta H. So, this will be now used to integrate it with the GCC. Now, if I see a distillation column, this may be my top tray with a T1 temperature, then the temperature T2, T3, T4, T5, T6, and if this is the pinch, then delta T H is handled by this, and Q1 is passes through T2, Q2 passes through T3, and if T4 is the pinch, then Q3 is 0. Now, if I see this region of the distillation column, so this works as a sink, and this region of the distillation column works as a source. So, this is the steam temperature at the reboiler, and this is the cooling water temperature at the condenser. So, within these two temperature levels, all the distillation column plates are working. So, these are the temperature intervals, heat cascade and sink and source area of distillation column. Now, how the integration of a column with background process will take place? Now, this is my background process, this is the GCC of my background process. This GCC clearly tells that you need a hot utility at T1 temperature and you need a cold utility at T2 temperature. The hot utility is servicing these streams, this is heating the stream from this to this. this part is that the process stream is giving heat to the another process stream, and from here to here again heating takes place using the utility. But here we see there is a large delta T available and which decreases when we go to this. Now, by integrating a distillation column here under this large delta T, I can make the distillation column operation almost free of cost. Now, let us see how. This is under a T and delta H diagram. So, for integration of distillation column with upper pinch region, the condition should be that T 1 should be greater than T reboiler and T condenser should be greater than pinch. So, this is the upper region from pinch to T 1. So, this T reboiler temperature should be less than T 1 and T condenser temperature should be more than pinch. So, this is the T reboiler and T condenser temperature. Now, this goes and it can be integrated now. So, what is happening practically? The hot utility is giving heat to the reboiler and then the condenser is giving heat to the streams which are available from here to here. So, with this stream, this heat, the streams available from at this point to this points are getting heated up. So, while this heat is cascading down, it goes through the distillation column. Now, what we are gaining out of it? That now this the distillation column is running free of cost, whereas this background process is also running with the help of the same utility, hot utility. So, by integrating this distillation column above the pinch, I am basically running this distillation column almost free of cost. So, we can conclude that by integrating a column with the background process, either the column will run free of cost or it will be in a position to decrease the amount of hot utility. Now, similarly, this part of the column can be integrated below the pinch, and in that case T pinch will be greater than T reboiler and T condenser will be greater than T 2. So, this can be integrated here also. So, integration to save energy. Why we are doing integration? To integrate to save energy requirement of reboiler of distillation column, and also cooling utility we are also saving. Now, the distillation column can be integrated above the pinch or it can be integrated across the pinch. When it is integrated across the pinch, it takes Q reboiler from above the pinch area and rejects Q condenser in the below the pinch area. When it does so, we call it that it is being integrated across the pinch, or it can be integrated below the pinch. In the below the pinch, it is taking Q reboiler from below the pinch and injecting Q condenser below the pinch. So, let us see that whether these three conditions are favorable to us or not. We will analyze one by one. Now, this is a distillation column which is integrated above the pinch. In the above the pinch, it is a sink. That means, it takes heat from outside. Now, if I am integrated a distillation column here, so it will take heat from here. So, if it takes heat from here, it will load the system, because in the sink it comes from outside. When it rejects heat to this, then it is decreasing the heat load of the sink. So, the heat load is now Q H minimum plus Q reboiler minus Q condenser, because Q condenser is giving heat to above the pinch area, Q reboiler is taking out, that is why it is being added to this, and Q condenser is giving this heat. So, it is deducted from it. So, total heat required to run this distillation column as well as to service the above pinch area is QH minimum plus Q reboiler minus Q condenser. Whereas, below the pinch area QC minimum is rejected to cold water. So, it is not changing. When I am integrating this distillation column above the pinch area, this is only affecting the hot utility consumption and it is not affecting the cold utility consumption. So, let us analyze. So, overall utility consumption is Q reboiler plus QH minimum minus Q condenser. If we consider Q reboiler is equal to Q condenser, then the distillation column will run free of cost. And if Q reboiler is little bit greater than Q condenser, then obviously this distillation column will run with a little addition of hot utility. That means, it will load the system, but the load will be very less, because Q reboiler is almost equal to Q condenser in a distillation column. So, what we observed here, that if the distillation column is integrated above the pinch, then the distillation column runs almost free of cost. So, we are now able to save the hot utility as well as cold utility, which is otherwise utilized for a distillation column. So, the recommendation will be above the pinch, yes, distillation column can be integrated above the pinch and it will going to do the to benefit us. Similarly, we see now a second case. Now, let us see the exactly what is happening here. This is process GCC. I have integrated this above the pinch. From this part of the hot utility heat is coming through the reboiler to this distillation column, and this part condenser is rejecting heat to this streams which are available from this part to this part. Now, how physically this will look like? The streams here, the process streams here will go through the condenser to pick up the heat, and the hot utility which is being used here will be used in the reboiler. So, hot utility will hit the reboiler and the process streams will be used in the condenser to cool the condenser. Now, this part of the hot utility is servicing this part and this part of the GCC. This is how it will be integrated physically. Now, this may second case is shows that the integration can be like this, but this is not considered to be a very good integration, because the hot utility requirement increases. The hot utility which is here to here, they goes to the reboiler and then to condenser, and condenser sends this heat to the cooling water, which is a cold utility. So, the cold utility requirement and hot utility requirement increases, but this is partially serviced by the hot utility here, not fully, but partially. That means, hot utility which is available here will service this part of the reboiler, and the condenser heat of this part will go to the process streams. So, this is how in actual practice this will be integrated with the process GCC. Now, let us take another condition. We have discussed that if the distillation column will be integrated above the pinch, then distillation column will run free of cost. It appears that this is the only one condition. that it has to be integrated above the pinch, but there are some other conditions too, like when these are the different temperature levels. Say at this temperature level the heat requirement is Q 1 plus Q reboiler minus Q condenser. When I take Q reboiler at this temperature level, I deduct Q reboiler here. So, this and this cancels out. So, only Q 2 minus Q condenser remains. Now, if the Q condenser is more than Q 2, then at this temperature level the system will not work. Similarly, here Q 3 minus Q condenser. So, Q condenser should be less than Q 3 and Q condenser should be less than Q 2 for this temperature levels to be feasible. Here I eject Q condenser here. So, this cancels out. So, there is another limit, there is a limit on the heat load that can be borrowed from any process. Sufficient heat flow must remain in the process at all temperatures spanned by the column. The requirement is that Q 2 and Q 3 are greater than Q condenser prior to integration of the column. So, this is our condition that Q 2 and Q 3 should be more than the Q condenser individually before integration of this column. Now, if it is not satisfied, then this integration cannot take place. If the condenser is only to be integrated, as can be seen, all heat flows above the condenser temperature must be greater than the Q condenser. Now, if it works like this, that hot utility is given here as well as here Q reboiler. So, hot utility requirement here will be Q H minimum minus Q condenser, because Q condenser is ejecting heat inside this above the pinch area. Now, if it is so, then the heat flow should not be negative, this has to be taken care of, then only a integration can take place. This is partially, this column is partially integrated, it is not taking Q reboiler from upper pinch area, it is only injecting the Q condenser to the upper pinch area. Now, let us integrate the distillation column below the pinch. Now, when I integrate this, Q reboiler is this heat is taken from the below the pinch area. Now, I can very easily take heat from here, because this is a source now and source has extra heat available with it. So, I am using that extra heat here. Then I am also injecting the Q condenser here. So, my cooling requirement will be Q C minimum minus Q reboiler plus Q condenser. However, at the same time my Q H minimum will remain unaltered, because I am not changing the thermal balance here and it is in thermal balance. So, my cold utility requirement is now this. So, the overall cold utility consumption is Q condenser plus Q C minimum minus Q reboiler. Now, if we consider the Q reboiler is equal to Q condenser, then the distillation column will run again free of cost. If Q reboiler is little bit more than the Q condenser, then also this will reduce to some extent Q C minimum. So, what we conclude out of it, that if the distillation column is operated below the pinch also, in most of the cases either a little bit of less or more utility will be required, but for all practical purposes the distillation column will run free of cost. So, the conclusion is, if the distillation column is placed below the pinch, this is yes, we can place below the pinch and it is going to benefit at least the distillation column, because this distillation column will now run free of cost. Now, the third part of it, that is across the pinch. Let us see what happens when I place a distillation column across the pinch. Now, let us see how this will be integrated below the pinch. This is physical aspect, let us see, then we will consider the placement across the pinch. So, when I am putting up a distillation column below the pinch, it will look like this. So, the heat which is available from here to here by the process streams will be given to reboiler, and the heat which is available from this to this is also given to the reboiler. This part of the process stream is giving heat to this part of the process stream, and a portion of this condenser of the distillation column is giving heat to this portion of the stream, process stream, and this portion of the condenser is pushing heat to the cold water. So, it is going to take heat from this portion, this part, and giving heat to the cold water. Now, this is another, we can also integrate like this. Here in the distillation column, the intermediate condenser is being used. So, a column with intermediate condenser placed below the pinch. So, the heat from this to this is coming to this area, and then this part of this heat goes to this cooling water, this part of the heat goes to this cooling water, and for this small part the heat is coming from above, this to this, and this part of the heat goes to this process streams from here to here. So, this shows a feasible integration of a distillation column below the pinch area. Now, this shows a intermediate condenser, this is a reboiler, and a part of vapor goes to this condenser, and then it is recycled back to the same column, and this is feed, and this is the original condenser. Now, if you see here that I am taking heat, reboiler heat from here. So, this is Q 5 minus reboiler, this comes Q 6 minus reboiler, these are the temperature levels, and here Q 7 minus reboiler plus condenser. Here at this temperature level I am adding condenser heat. Now, for these two conditions, this should not be negative, that means Q 5 and Q 6 should be individually greater than Q reboiler. So, my condition is this for the integration below the pinch. That means, the energy flow should not be negative in any case. Similarly, here partially I am doing integration. This is taking below the pinch Q reboiler heat, because this is a source. If I take heat from here, it will decrease my QC minimum, and it has decreased the QC minimum by Q reboiler amount. So, my cold utility has decreased, whereas my hot utilities remain same, and this condenser goes to the cold water again. So, if I am doing the partial integration, it is going to decrease the cold utility of the process. So, while analyzing this, we have to see that what is the utility consumption of the process as well as column at the start, when I am operating them without integrating each other. Then after integration, I have to see that what is the utility consumption of the process as well as the column after integration. So, if I find some savings, then I can go for integration. Integrations can also increase the complexity. This has to be kept in mind also while going for integration. Now, here I am integrating the distillation column across the pinch. Now, when I am integrating this, I am taking Q reboiler, that means the heat required for the reboiler from above the pinch area. So, my hot utility consumption increases by Q reboiler. So, Q H minimum plus Q reboiler, because is this area the system is deficient of heat, and that is why I am taking heat from outside. So, if I take heat further from here, so this outside heat has to increase to satisfy this. So, my hot utility requirement has increased from Q H minimum to Q plus reboiler. Similarly, I am rejecting a heat to a area which is a source area, that means it has got more heat than required. So, the cold utility, this will obviously this heat will go to the cold utility, and that is why the cold utility amount has increased from Q C minimum to Q C minimum plus Q condenser. Now, if I see separately, if I operate the system and distillation column, this is the amount of hot utility and cold utility I will be consumed. So, I am not getting any benefit out of it, and that is why the third recommendation is that we should not place a distillation column across the pinch. So, if I conclude, the placement positions above the pinch, distillation column can be placed, it will run almost free of cost. Below the pinch, yes, it will run almost free of cost, but across the pinch, no. So, we will not like to place a heat exchanger across the pinch. But while telling this, that if I tell that I should not place it, this will not solve the problem, because if the distillation column temperature levels are such, Q reboiler and Q condenser are such that it falls across the pinch, then we have to place it across the pinch. In that scenario, what should be done? You will see that we have to increase the pressure of the distillation column to take it to either above the pinch area or to decrease its pressure to bring it to the below pinch area. When I am increasing the temperature or decreasing the temperature of the distillation column, I am basically affecting the Q reboiler and Q condenser. And if I change the Q reboiler or Q condenser by changing the pressure inside the distillation column such that it either falls above the pinch or falls below the pinch, then I may solve my problem, which will appears due to the placement of distillation column across the pinch. So, we will see that what are the different parameters which are available in the hand of the designer, so that by manipulating those prior parameters a proper placement can be designed. Now, this shows across the pinch. So, this is placed across the pinch. If you see physically, this is the hot utility requirement for the distillation column, which goes to the reboiler, and then the condenser ejects the same heat to the cooling water or the cold utility. And this is the amount of hot utility which is required to service the GCC of this process. So, here what we see that the total hot utility requirement is the hot utility requirement for the distillation column up to this, plus for the GCC which is up to this. Similarly, the cold utility requirement for the column is this. If I project this point here up to this, and cold utility requirement for the GCCs from here to here. So, here I am not getting any savings when I place a distillation column across the pinch. However, if we see here, there is no chance of negative flow of it, because this quantity are positive. So, as far as the distillation column across the pinch is concerned, it is not going to make any heat flow negative in any temperature level. But a distillation column placed across the pinch is a improperly placed distillation column. Now, it is now clear that provided a distillation column operates away from the pinch and there is sufficient heat flow available, only marginal or no extra utilities are required for the operation of a integrated distillation column. This we have seen very clearly that for the upper pinch area, if it is integrated, it almost runs free of cost or with marginal increase in the utility. If either of these conditions are not satisfied, then one can alter the column condition to make integration possible away from the pinch. If I am not able to satisfy this condition, that is neither it is falling on above the pinch or below the pinch, it is falling across the pinch, then column conditions has to be changed to make it fall on either side of the pinch. Now, there are many methods to do it, and those methods are pressure changes, split column loads, thermal coupling and immediate reboiler and condensers. So, or intermediate reboilers and condensers. By applying these techniques, we can properly integrate a distillation column with process GCC. Now, let us see what are the effects of altering column configurations. It is required to know that how it is going to affect the distillation column if I am changing its operating parameters. Now, if I change the pressure, what will happen? Say this is across the pinch. If I increase its pressure, the reboiler temperature will go up and condenser temperature will go up. So, this will shift to this region. If the column is placed across the pinch, one can either increase or decrease the pressure as it affects T reboiler and T condenser to change the column's position relative to the pinch. That means, changing this pressure, I can either shift it the upper side or decreasing the pressure, I can go downside. In both of the cases, I will be able to integrate it properly, because if it is integrated above the pinch, it is considered to be good integration. If it is integrated below the pinch, it is also a good integration, because above the pinch and below the pinch it will be profitable integration. Now, let us see, if it moves up, it now starts saving the hot utility. In the earlier case, it was not able to save the hot utility. It can also be taken down, it now saves the cold utility. At this position, it will run free of cost, at this position also it will run free of cost. Now, this was improperly placed earlier, because it was cutting this line. Now, by increasing the pressure, it can go up. Now, it is beautifully fits into the GCC. So, by changing the pressure, I can tailor the position of the distillation column in the GCC, or I can move to such a area where it better fits the GCC. Now, the effect of increased pressure. If I am increasing the pressure of a distillation column, it will have its own effect. Now, let us see what happens. If basically when I am increasing the pressure, the temperature of every tray of the distillation column will increase. Now, if it is so, then what will happen to the separation of the separation which is being done in the distillation column. Separation will generally become more difficult. Why? With higher pressure the relative volatility decreases, and if it is so, then it will require either more plates or a large reflux ratio to do the same separation. The second point is, with increase in pressure, the latent heat of vaporization decreases, compensating to some extent the increased reflux ratio. Because the latent heat of vaporization will decrease, with the same amount of Q being transferred to the condenser, more liquid will be formed, and hence reflux ratio can increase. The increase in number of plates is offsetted by the reduction in column diameter because of increased vapor density. Now, when we increase the pressure, the density of the vapor decreases, and due to this the size of the column, that means the diameter of the column will decrease, though the number of plates will increase, that means the height of the column will increase. But due to the reduction in the diameter of the column, the fixed cost of the column will be compensated to some extent. Now, these conflicting trends which has been discussed in point number 1, 2 and 3 usually result in little variation in column costs with increase in pressure until some upper limit is reached. When we design a column, it is designed for a upper limit. So, I cannot go beyond that upper limit. If I go beyond that, the column can burst. So, there is a upper limit to each design. This limit will probably be defined by an unacceptably high reboiler temperature, either because of thermal decomposition of the bottom product or because of the lack of the sufficiently hot heating medium required for it. That means, there are other constraints also. I cannot increase the distillation column's pressure more than a limit, because the thickness of the distillation column will decide the pressure. The second problem which will come, that it will have a higher reboiler temperature, and due to this thermal decomposition can take place in the reboiler. So, if it goes for thermal decomposition, so obviously I cannot operate the reboiler at those temperatures. The third will be that I may not get a sufficiently hot heating medium to operate the reboiler at such a higher temperature. So, these are some constraints which one will face when it increases the pressure of the distillation column. Now, what will be the effect of decreasing pressure? Here one aims to integrate the column by decreasing its temperature. If I decrease the temperature, the reboiler temperature as well as condenser temperature will fall. So, it will move downward and I may integrate it below the pinch area. At low pressure in general, the separation is easier. Lower limit exists, however, and are usually fixed either by the desire to avoid refrigeration or by a reluctance to operate under vacuum. If I operate under vacuum, the velocities increase, the column diameter will increase, the pipe diameters will increase, and maybe that in the condenser I have to use a refrigeration. So, these are the different problems which we will face when we decrease the pressure. So, the pressure can be manipulated, but to some extent. The splitting of column loads by increasing or the decreasing pressure, if my problem is not solved, then what is the way out? The way out is that split the column into two parts and place one part above the pinch and the second part below the pinch. So, let us see how this is being done. It may be that even after all possible pressure changes have been explored, there is no position which can totally accommodate the distillation heat load. In such a situation, one possibility is to split the column load into two or more small loads. The pressure of each column must then be chosen such that no column operate across the pinch, and all intermediate heat flows in the cascade are positive. These two conditions we have to meet. However, two columns will be more expensive than one in terms of the capital. The extra cost must be offset against the savings in the energy. So, when I am going for a split column, then I am increasing the complexity of the design, and once this complexity increases, the capital cost will also increase. So, I have to see a trade off, that whether by doing so my savings are appreciable or not. Let us see how physically the splitting will be done. A distillation column is now splitted into two parts, column number 1 and column number 2. The feed is also splitted, one part is going to column number 1, the other part is going to column number 2. Now, this bottom product from the column 1 is coming out here, the bottom product from column 1 is coming out here, it is joined with column 2 and I am getting the bottom product here. Similarly, the top product of the column 2 goes to condenser 2 and top product of the column 1 goes to condenser 1, and they are joined here and I am getting the top product here. A part of this condensed liquid is used as refluxing 1, a part of condenser 2 is used as refluxing in the 2. Now, as far as splitting is concerned, there are two different distillation columns here and that product are then joined to find out the final product. So, these two columns can be operated at different pressures such that their evaporator, that is reboiler, and condenser pressures or temperatures of one falls in the upper pinch area and the second falls in the below pinch area. So, here this is the process which requires QH minimum and QC minimum as hot and cold utilities. When I integrate column 1, this part here, I take Q reboiler 1 from this and send the Q condenser 1. Similarly, I take Q reboiler 2 and Q condenser 2 to this. Now, if the flow of heat inside this system or the columns are positive, this integration can be done very easily. Now, if I see here, the Q hot requirement is QH minimum plus Q reboiler minus Q condenser, and if Q reboiler 1 is almost equal to Q condenser 1, then they cancel each other and this distillation column 1 is operating free of cost. Similarly, if I see the cold utility, it comes out to be QC minimum minus Q reboiler 2 plus Q condenser 2. So, if Q reboiler 2 is equal to Q condenser 2, they cancel out and my QC minimum remains, which is the cold utility of the process. So, this column 2 is also running free of cost. So, by splitting a single column into two columns and then adjusting these two columns somewhere in the upper region of the pinch or below region of the pinch, I can solve the problem of the case when distillation columns falls across the pinch. The same is shown here, this is the distillation column. this is not fitting into the GCC. I break it into 2 columns and then place one column above the pinch and the second column below the pinch. And while doing so, these 2 columns run almost free of cost. This is the second, where both the columns can be put above the pinch, because there is sufficient delta T available here and both the columns can be put here, one above other, and utilize the upper pinch area. So, this is how by splitting the columns we can fit those columns into the GCC and run the columns almost free of cost. Now, there is another process through which this can be done. It is called thermal coupling. A alternative solution when heat flows are limiting, integration possibility is to reduce the heat load by thermal coupling. Thermal coupling is possible when multi-column arrangements producing a number of products from a multi-component mixture. Now, this shows a part of it, that there are 3 components into the feed A, B, C. In the first column, I am separating A and B C. So, B C goes at bottom product and A comes out as top product. Then this B C is separated in terms of B and C in the second column. Now, if I see the temperature levels here, so my reboiler 1 has this temperature level, the reboiler of this, and condenser 1 is this temperature level, and for this 2 the reboiler 2 is this temperature level and condenser 2 is this temperature level. Now, its side stream rectifier is shown below. Here there is a column where A, B, C goes into the feed, A comes out as a top product, then a part of the vapor from A is drawn here and then goes to a rectification column, and it separates B, and a part of it is written here, and at the bottom I get C. So, a side stream rectifier is shown here. All of these arrangements consist of 2 columns coupled via liquid and vapor side streams. This coupling eliminates at least one reboiler. So, here if I see, this is the reboiler 1 and there are 2 condensers 1 and 2, the condenser number 2 and condenser number 1. So, it eliminates one reboiler and reduces the total heat load to be handled. Thus, if the flow in the cascade are limiting, integration opportunities using thermal coupling is worth considering. We have seen that it is not that only where the distillation column is placed above or below the pinch or across the pinch. The heat flows has to be also checked. If the heat flows becomes negative, then coupling is not possible. So, here in those cases the thermal coupling is worth considering. Now, let us see the intermediate reboilers and condensers. Now, if across the pinch I am placing the reboilers and condensers, if changing the pressure of the column is difficult to achieve, then what is the way out? In this case, intermediate reboilers or condensers can be used to get at least some of the saving resulting from good integration. If I am not able to find out the complete saving by integration, as we have seen in the case of integrating the distillation column above the pinch or below the pinch. If I am not finding the complete integration or complete saving, then I should go for partial saving, and this partial savings can be done using intermediate reboilers and condensers. The column is operating across the pinch and heat added to the reboiler is Q reboiler. This is Q reboiler. Q condenser is removed from the overhead condenser below the pinch, but Q intermediate condenser is removed above the pinch. So, it is taking the heat here from here, the Q reboiler, and in an intermediate condenser the heat is rejected to the above pinch area through this intermediate condenser. So, it rejects the heat above pinch area and rest of the heat is put into below pinch area. So, if I see the hot utility demand here, this is Q H minimum plus Q reboiler minus Q intermediate condenser. So, at least the hot utility demand has decreased by Q intermediate reboiler here, and the cold utility demand has been the QC minimum plus Q condenser. Otherwise, the whole condenser load was Q intermediate condenser plus Q condenser. So, if I say see the hot utility demand has decreased and the cold utility demand has also increased in comparison to operating the process and distillation column separately. So, partial saving is done. Exact utility is needed to run, extra utility is needed to run the column, but not so much as the total load. This we have seen. Thus, with a column forced to operate across the pinch, it is still possible to rescue some heat and reduce the utility requirements of the overall process, at least partly, by good integration. Now, if there is a insufficient heat flow, that we have seen that insufficient heat flow, like here I will show you the picture here. The condition is that Q 3 should be more than Q condenser, and here the Q 2 should be more than Q condenser here when I am integrating above the pinch. So, if Q 2 becomes less than Q condenser, then this operation will cease. So, in such cases what will be done? If a distillation column is not operating across the pinch, but there is insufficient heat flow at some temperature levels in the cascade to integrate the total loads, then again intermediate reboiling and condensing may provide a remedy. Now, here if you see is a intermediate condenser, here I am injecting heat in two parts. That means, I am not injecting heat at one go, like there we have seen that Q 2 minus Q condenser, where Q condenser is the summation of this Q intermediate and Q condenser. So, if I break this load into 2-3 parts, then again I can guarantee heat flows. So, this is what it is shown here. If a distillation column is not operating across the pinch, but there is insufficient heat flow at some temperature levels in the cascade to integrate the total load, then again intermediate reboiling and condensing may prove a remedy. Below the pinch, the logic is analogous. Here I have shown you above the pinch. Similarly, below the pinch I can have the same logic. We can use intermediate reboilers to ensure that the cascade heat flow remains positive. There we will use intermediate reboilers in case of intermediate coolers, as has been used in the upper part of the pinch. But this will increase the capital cost, and this increase in capital cost against the savings. So, a trade off between these two has to be found out, and if the savings are more, then we can go for intermediate reboilers and condensers. So, these are the references, and thank you.